Welcome to the pre-lab lecture video on mass spectrometry. So this technique is sometimes called mass spec or MS, and it's a very powerful analytical technique to establish the identity of compounds. The way that we do this is by actually indirectly measuring the masses of those compounds within one of your samples. So the way most mass spec instruments work, although the instrument design can vary depending on the kind of technique that you're using, is that you'll have some kind of a path shown here as kind of a curved tube. We're going to go ahead and call this the sock of science because, well, that's what it looks like to me. And on one end of this tube, your sample gets injected and is subsequently ionized. This part's crucial. So compounds that you inject as neutral species will become usually positively charged, so they become cations. And then they're passed through a couple of plates that accelerate them into a beam toward this bend in the path, which is why I think this looks like a sock. And so you can see these paths shown in turquoise in the image on the slide. What ends up happening, though, is that there's a bend here as well as a magnet that's placed very precisely at the bend. And we know from our conversation about NMR that charged particles like cations are going to interact with a magnetic field. So what ends up happening is that those charged particles would go straight into the sidewall of the tube here, but because they're actually interacting with a magnetic field, the trajectories bend so they can actually make the turn and get down to the detector at the other end of the path. But we also know that these charged particles, even though they're small, they have momentum because they're moving. But the momentum is going to be dependent on the mass of the particle. Like heavier particles will have more momentum and lighter particles will have less momentum. So if we think about what's going to happen when we go into this curved part of our tube sock, the heavier particles, their trajectories will be bent by the magnet, but by less because they have more momentum. They're not as heavily impacted by the magnet, and they actually end up at what we would think of as like the top of the detector in the way that this image is configured. Lighter particles will actually get their trajectories bent more, and so they'll collide with the way we would think about like the bottom of the detector in this image. So basically what we're looking at is where this charged particle impacts the detector correlates with the mass of that particle. So we're basically looking at addresses on this detector screen where charged particles will hit, and we can correlate where those hits happen with mass. But we don't actually obtain a mass directly. It's not like we can get from the instrument like 109 grams. Instead, what we get is called a mass to charge ratio, right? So we're actually looking at the mass of the particles divided by the charge. And I think this makes sense because if we make the charged particles more charged, like a +3 cation instead of a +1 cation, then they would actually interact with the magnetic field more strongly, and that would actually change the way their trajectory bends within that curved part where the magnet is. So remember that we're measuring an M/Z or an MZ ratio. For small organic molecules, M/Z is usually fairly simple because Z is almost always 1. It's very difficult for us to end up with more than one positive charge on a small structure, especially something that's organic. But you could imagine that if you actually did mass spec with inorganic substances containing metals, that your Z could be some other number. We know lots of metals that have charges that are +2 or +3 or +4. The same thing is true for larger molecules like proteins or other biological species, where we would actually think about the ability to have many, many positive charges because the structures are so large. And in that case, Z can become very important. So one of the most critical parts about mass spec is the way in which we ionize the compounds that we inject into our instrument. Now, there's a few ways to do this. There are actually many more than are listed here on the slide, but some of the more common ones are electron ionization, or EI, chemical ionization, or CI, and electrospray ionization, or ESI. So we'll talk mostly about electron ionization first, because most of the data that you'll be working with in this lab and that you would actually be observing on instruments at LMU is all obtained using EI ionization. And this actually works in a fairly simple way, where we're actually going to use an electron a little bit like a billiard ball, or if we were playing pool, that electron is going to knock another electron out of a molecule, and that's going to leave behind a positive charge along with an unpaired electron. So if you imagine doing this on, like, say, a lone pair, you start with 2 electrons, you knock one of those electrons out, and that leaves behind a single electron, so a radical, and you end up with a positive charge, so the thing is overall a cation. We call these species radical cations. So let's actually look at what this ionization process would look like for a simple organic molecule. We'll just look at methane, so CH4. And you can see that I've listed a few pieces of information that will become important for us as we actually start to interpret mass spec. We have a total number of electrons, the molecular weight of methane itself, as well as the M/Z ratio for methane itself, in this case prior to ionization. So we know the mass is 16 AMU, but the charge is 0, and so our M/Z ratio is 0. That means we would actually not observe CH4 without ionization by mass spec. This is why ionization is so critical. So let's actually do our electron pool game, and we'll knock out one electron to make a radical cation of methane. So we don't really know where the electron came out. We're going to depict CH4 as a structure. One of the bonds contains only one electron, so we actually just write this kind of bracket notation and then dot and a plus to indicate a radical cation. So this is what's called the molecular ion, because we actually have all of the same atoms from our substrate, but we just lost an electron. So now we've got 9 electrons. The molecular weight of this ion is still 16. The M/Z ratio is now 16 divided by 1, and we do observe this by mass spec, right? So again, depending on where this particular ion hits our detector, we could work backwards to decide, okay, the M/Z ratio for that collision or that impact on the detector is 16. So one of the issues that we also encounter, especially in EI, is that these molecular ions tend not to be very stable. And so they start to what's called fragment, or shed atoms or whole groups of atoms as they travel down the detector. So you can imagine this a little bit like having your molecular ion traveling down that tube sock, but before it gets to the bend, it actually falls apart into more different kinds of species. And then each of those independent ions goes through the bend and then lands in a different place of the detector. So in this case, we would think about being able to observe both a molecular ion as well as a fragment ion where a hydrogen radical is lost to form the CH3 plus species. So now we no longer have a radical cation, we just have the methyl carbocation. So there's 8 electrons here. We've lost a hydrogen atom, so our molecular weight for the ion is now different. It's 15. And because we're still having just one positive charge, our M/Z ratio is also 15. Okay, so if we actually look at the mass spectrum of methane, this is actually what we observe. So you can see that there's a set of different lines on an x-axis. The x-axis is M/Z, so we've got different kinds of values here. For us, we're going to be using essentially what's called low-resolution mass spectrometry, so we'll be looking at just whole numbers for M/Z ratios. But there's much more sophisticated techniques now where you can actually work out to 4 or even 5 decimal places for this M/Z ratio. On the y-axis, we have what's called relative intensity. This is essentially a count of how many collisions in a particular spot of the detector were observed. So another way of thinking about that is the population of the different ions that formed after that initial ionization event at the far end of our tube sock. So here we see that the most common ion that hits the detector has an M/Z ratio of 16, and that turns out to be our molecular ion, the radical cation of methane. But we see that there's almost as much of this fragment ion, the CH3 plus species, where we have an M/Z of 15. And then you can also see that this species continues to fragment by losing more hydrogen atoms to get to an M/Z of 14, 13, or even, which is a little bit shocking, just carbon with a positive charge. Okay, so this is what a very simple mass spectrum looks like. We could also look at more complex structures, so let's also look at the mass spectrum of acetone. So here you can see a few things right off the bat. One is that I've got more types of ions, and that's not necessarily too surprising because there's a lot more bonds that could break, a lot more types of fragments that could form. But one of the other things that you probably notice here is that there are 2 ions that seem to be much more prevalent than anything else. And so I've actually labeled the M/Z values for those 2 peaks. You can see one is at 58 M/Z and the other is at 43. So the M/Z ratio of 58, that actually corresponds to the molecular ion of acetone itself, excuse me, the radical cation here that I'm showing on the left-hand side of the slide. On the other hand, the M/Z ratio signal of 43, that's lighter than acetone itself, And in particular, the difference between the molecular ion's weight, so 58, and the M/Z ratio of the peak that we're looking at, 43, can be helpful. So 58 minus 43 is 15, which tells me that we must be losing a CH3 group, right? M/Z of 15, or more specifically a molecular weight of 15, corresponds to 1 carbon and 3 hydrogens. So it's likely that we're losing a methyl group, and that means that we must be leaving behind something that's positively charged, because we are observing it in mass spec, that has 43 AMU as its mass, or an M/Z ratio of 43. So if the structure of acetone is what I think it is, then the thing that would make sense to me is to actually cleave the carbon-carbon bond between a methyl group and the carbonyl to give rise to what's called the acetyl cation, which you can see here with an M/Z ratio of 43. Okay, so we can look at another type of example here. We'll look at the EI mass spec of triethylamine, and I've shown you the structure of its molecular ion on the left, where one of the electrons from the nitrogen lone pair has been knocked out, and that gives us a mass over charge ratio of 101. So looking at the mass spectrum that's obtained experimentally, we can find that signal near the far right, and then we can see a set of other types of fragments that are also forming before hitting the detector here. Normally it's only going to be possible for us to reason through a few of these more major fragments, and so we'll go ahead and do that, working from right to left. So this signal that turns out to have an M/Z ratio of 86 is the most prevalent ion to hit the detector. And so again, we can see that if we're starting with an M/Z of 101 and ending up with 86, we're losing 15. That corresponds to loss of a methyl group. And so I can actually work out the structure of the cation that formed after fragmentation of the molecular ion. So one of the things that I can also think about is that some of these positive charges I might be able to make by fragmentation are more stable than others. And that might be related to how much of that ion is formed. If I actually get a lot of it, then I would expect to see a lot of it in the detector, a very large signal. But the only reason why that would be true is if actually that cation was fairly stabilized. And we can see here that this nitrogen cation could be resonance stabilized by electrons from nitrogen itself, which should be like unusually good for any of the other possible positive charges I can end up with in this molecule. All right, so we see that there are also some lighter fragments. So we'll look at one other one. We could look at the M/Z of 58 and work out that from 86, so from one of these fragments, we're losing an additional 28 AMU, which corresponds to 2 CH2 groups, or CH2, CH2. So one way to make sense of that is the loss of an ethyl group and then the transfer of 1 hydrogen from the ethyl group onto the nitrogen itself. That would give me an M/Z ratio of 58. So one of the things to take away from this slide is that fragments can also fragment. Typically, it's helpful to work these spectra from right to left. You're more likely to find molecular ions on the far right, and then the things that are a little bit closer to the right-hand side of the spectrum are going to be usually resulting from single fragmentation. So I also want to introduce the concept of the nitrogen rule when we're looking at the mass spec of triethylamine. And there's actually 2 different rules that are floating around out there. So if you look at different videos on YouTube, or if you look at your Morag book, which I recommend, or if you look at other kinds of online resources, you'll see different kinds of statements. If you're describing molecular ions, right, so all the atoms from the sample itself, but you've just lost the 1 electron, then if you have an odd M/Z ratio, then you have an odd number of nitrogens. So in our example, our M/Z is 101. That's an odd number. And we have an odd number of nitrogens. Well, 1 is an odd number, so that works out. For fragment ions, there's a slightly different kind of a rule. There you'll see an even M/Z if you have an odd number of nitrogens. So you can see in our fragments here, we have 86 and 58. Those are both even numbers. And in both cases, we've got the 1 nitrogen, which is an odd number. So you can actually use this nitrogen rule right out of the gate looking at mass spectra to decide whether your compound has an odd or even number of nitrogens. All right, so we'll look at one other example of benzyl chloride. So again, I've shown you the radical cation of this species. That's going to give rise to the molecular ion. We've just knocked a lone pair off of the chlorine atom. But here we actually need to be careful because we actually know that there are two different kinds of chlorine atoms that are relatively high abundance. There is the 35Cl isotope, which is about 75% of all chlorine atoms. If that's a part of the benzyl chloride molecule, then my M/Z ratio is 126. But if my benzyl chloride molecule has a 37Cl isotope, which is about 25% of all Cl atoms, then I have a different M/Z ratio. I have one of 128. So if we actually look carefully at the right-hand side of this mass spectrum, we find that we have that approximate 3-to-1 ratio of its signal intensities at 126 and 128 M/Z. And that's actually like an isotopic signature for a chlorine. So if we actually see this, where we've got two different signals that are separated by two M/Z numbers, so like 126 to 128, and that we have that relative intensity of 3-to-1, then that's very highly likely coming from some kind of a chlorine atom in the ion that we're actually observing. So I also want to assess fragments, and in here we can see that there's one fragment that's forming in preference to pretty much everything else, and that's the M/Z of 91. So if I subtract 135 from 126, I end up with 91. And that's indicative of simply losing the chlorine atom. And that would actually give us a resonance stabilized cation, so the so-called benzyl cation. So we would kind of expect for this to be like a sink where all of these fragments are trying to get, because if you're going to be bearing a positive charge, this might be the best you can do for this kind of a structure. You'll also note that there's no longer that isotopic signature present, and that's because the chlorine atom is no longer a part of the fragment, right? So here we're only going to get an M/Z of 91. All right, so we can also talk about different kinds of ionization methods briefly. Chemical ionization is kind of a boutique technique, so really what I want you to be aware of is that it exists. Electrospray ionization, or ESI, is quite common now. In fact, it's rapidly supplanting EI for the characterization of complex molecules like proteins, or even complex organic structures. We still don't entirely understand the physics about how ionization occurs, but typically the way we think about this is that your structure or your sample compound will associate to a proton or Na plus or K plus or whatever else you have to form a cluster that actually hits the detector together. So rather than actually like knocking an electron out of a substance, you're getting a positive charge by having your sample associate to something that's already positive charge or already has a positive charge, and that cluster is also going to be positively charged. So one of the things that's kind of cool about ESI is that you see very little fragmentation. So you can look at the exact same compound, characterized both by EI mass spec along with ESI mass spec. So EI is on the top, and you can see all of the different kinds of fragments that are forming. So lots of different peaks on the x-axis. But if you look down at the ESI mass spec, again, the x-axis is still M/Z, but you only see what looks to me like one fragment. Remember, we've got a chlorine atom, so we should be seeing two different peaks for a single kind of a fragment, and one molecular ion at 126 M/Z. So ESI mass spec is really useful for compounds that ionize so strongly that you can no longer observe the molecular ion. This can be a problem sometimes. Or if you've got a compound that's just very sensitive. It's also the case that what are called high-resolution mass spectrometry techniques. So this is where your M/Z ratio would be not whole numbers, but out to 4 or 5 decimal places. Those are almost always going to operate using ESI mass spec types of techniques. Okay, so finally, I think it might be helpful for us to actually work through the EIMS of an unknown compound so you can get a sense for how I approach mass spec data where I actually need to interpret it to assign the structure of a compound. So I'm going to start by picking out all of the major peaks or the major fragments. I'm not going to try to assign structures to everything. And I'm just going to make sure I know what their M/Z ratios actually are, because sometimes with the x-axis, the way I'm showing it in some of these examples, it can be a little bit hard to see. So you can see those numbers on the slide, and I ask 3 questions. Do I see any characteristic isotopic signatures? So do I have a chlorine or a bromine, or maybe something else that has a very characteristic isotopic abundant signature? Here I don't. I also think about, well, do I know the molecular ion mass? Do I observe it? And you can never know for sure, but I do have a peak at 149, which is essentially the heaviest fragment that exists in this for this compound. So I'm going to go ahead and assume that that's the molecular ion for now. And then the last question is whether I have a nitrogen or not. So I'm again going to apply the nitrogen rule both to what I think the molecular ion is, so 149. That's an odd number, and that means that I've got an odd number of nitrogens. So 1, 3, 5. Usually I'll make the assumption initially that I've got one nitrogen until I'm proven wrong. So I'm also looking at all of the fragments, and I see that some of them appear to be even. So at 106, we have an even fragment, and we know that that corresponds to an odd number of nitrogens. So the fragment with 106 m over z contains the nitrogen. The fragment with 91 m over z has an even number of nitrogens, which could correspond to having no nitrogens. And then the signal at 43 m over z, that also appears to not have any nitrogens present. So just to recap, I know that there's no halogens essentially because I'm not seeing any isotopic signatures that give it away. I'm going to assume that the molecular ion has a mass of 149, and I'm going to assume that I have a nitrogen. I don't know how many, but the patterns that I'm seeing by applying the nitrogen rule to all of my different peaks suggest that there is probably one nitrogen, but there could be more. Okay, so the next things that I'm going to do are to actually try to assign structures to these major fragments, and then once I actually have some structures for the fragments themselves, maybe I could use what I know about bond breaking and charge stability to work backwards and actually reassemble the fragments into a whole structure. Okay, so we're going to split screen here. You can see on the right the mass spectrum of the unknown compound along with labeled peaks for some of the more prevalent ions. And so we've talked a little bit already about what might be true about the structure. We know that there's probably not a chlorine or a bromine. We know that there's probably at least one nitrogen, and we know that the molecular ion probably has a molecular weight of 149. And so the next thing I'm actually going to try to do is assign signals, or assign structures, excuse me, to some of these more major signals. The first thing I'll do when I'm thinking about this is look for m over z ratios that sound familiar, because it turns out that there are some kinds of bonds in organic compounds that are far more likely to break whenever they're present in mass spec. So I'm just going to start by choosing to discuss the signal at 43 m over z. We've actually seen this in this pre-lab lecture. This corresponds to 2 carbons, 3 hydrogens, and an oxygen, or the acetyl cation. And so what's helpful here is that I know that the sample that I actually injected into the instrument had some kind of an acetyl group in its structure. So there must have been something attached to this carbon. We also can see that there's no nitrogen here, which is consistent with how we're thinking about the nitrogen rule. And then I can keep on moving. So this is like a fragment that's useful for me. I also recognize 91, right? And that's from the example that we looked at with benzyl chloride. This corresponds to the benzyl cation. So I know, in addition to the acetyl group, that I had the benzyl cation, or some type of a benzyl group, so there would have been a bond here that has broken, and that's where this fragment's coming from. So I can even start to think about, you might do this for NMR, for instance. Actually, let's do this in red. Like, this is the end of the fragment, this is the end of the fragment. So I'm going to think about connecting things here and here. One option would be to simply connect these 2 fragments together directly, but if I did that, my mass would actually be too low. I wouldn't get all the way up to the molecular ion, so there must be some other pieces that are missing. Notably, I have not done anything with nitrogen yet. So that's another thing that I want to be thinking about here, is introducing nitrogen atoms if I can. So what's left for me to do then is to think about 106. We know from the fact that this is almost assuredly a fragment ion and the fact that this is an even number that this contains a nitrogen. Okay, it's a heavier ion than this one is, and in fact, it probably contains this group just because this mass is so large. So I'm just going to try playing around with different things to see if I can draw an ion that like makes sense, that satisfies these criteria, right? It's the right mass over charge ratio, that it has a nitrogen. ChemDraw is great for this because you can draw the structure and then actually use the analysis tool to very quickly calculate molecular weights. Just make sure you put that positive charge in correctly, because otherwise you'll end up being one off, and that's from having an applied hydrogen where there shouldn't be one. And that's actually how I would normally do this if I weren't trying to like make a video or whatever. So instead I'm going to think about, well, 91 gets me to here. And then I need to think about finding an additional 15 AMU. So one option would be to just add a methyl group. 15 sounds like a methyl, but that's just going to give me a compound with no nitrogen. So I'm going to reject that. So this would be one option. As the radical cation, but no nitrogen. So that can't be right. Instead, I could think about something else attached to this part of my benzyl chain. Well, I need a nitrogen, so let's just throw one on there. Cool. So what I would do at this point is actually calculate the molecular weight of this drawing. So that means I've got 1, 2, 3, 4, 5, 6, 7 carbons, 1, 2, 3, 4, 5, 6, 7 hydrogens, and 1 nitrogen. If I add all that up, it's going to end up with 105. So, how would I add one more M/Z unit here? Well, I just add a proton. The only place I can do that is on the nitrogen. And I've got a positive charge somewhere. I'm just going to place it on the nitrogen. So this fragment corresponds to this molecular weight, or this M/Z ratio. And so now I have assigned structures that at least fit. This one's a little bit more speculative. These two are pretty rock solid. We see these kinds of ionization patterns all the time. And so now I need to kind of stitch together the structure here. So we've already figured out the relationship between this ion and this ion. And now we need to think about, well, where would this acetyl group go? So let's see. I could do this in a variety of ways. I could do trial and error. The other thing I could do is that if I've got these three fragments, if I have a fragment that's already fairly heavy, I could start to think about, well, what would the difference be to go from the molecular ion to this? Like, how much mass would I be losing? So that would be 149 minus 106. What I'm calculating is the molecular weight of what was lost to make this from the molecular ion, whatever my unknown structure was. And here I end up with, 43. So this is the piece. So that tells me that the thing that's connected to this carbon must be this nitrogen. And that if I now draw this structure that I can imply here, I actually hit the M/Z ratio that I want. 149 molecular weight. It looks like that might be cut off a little bit, so I'll rewrite it. Okay, so just to reiterate, the way that we ended up drawing this structure, which would correspond to our unknown structure or the molecular ion, was to use one of our heavier fragments to figure out, well, if the fragment weighs this and the molecular ion weighs a larger number, how much did I lose to get there? This is a convenient case where I can identify the last fragment in one of the other prevalent species that's forming in the mass spec. So what I'm basically thinking about is this kind of bond. If this is EI, maybe what's happening is that we're actually kicking an electron out of this bond, and then it can fragment in one of two ways. The remaining electron could go with the carbon, make a positively charged nitrogen, or the electron can go to the nitrogen. That nitrogen would be neutral, and then it would make us a positively charged carbon, which is the other ion here. So this is, in fact, the unknown structure, right? So you can see that there's a few techniques we use. Just to reiterate, we're going to start with simple unambiguous questions like the presence of some kinds of halogens. whether there's a nitrogen atom or if there is, how many. And then we would also want to make sure that we know where the molecular ion is. And then we have to basically use reference data or experience to work out common fragment pieces. So that could be things like the acetyl cation or the benzyl cation, as well as some trial and error, where we actually chart to figure out differences between masses and what kinds of structure those might correspond to. Again, I would strongly recommend that you use ChemDraw for that trial and error piece, because it speeds up your calculations and you can very quickly make changes, like delete a methyl group, for instance, and end up with a number right away where you're not having to recalculate by hand all the time. Okay, so what we're going to be doing in the lab then is basically setting you loose to work through a set of mass spectra where you're going to identify structures for the spectra, as well as structures of a few of the fragments that are observed. There's also going to be some reference data that's posted to Brightspace. So there'll be some isotopic signatures for different kinds of elements, like what kinds of intensity ratios you would expect to see for different kinds of elements, as well as the mass differences, right? So chlorine and then bromine, those might be different. And then finally, there'll also be a table of some common fragmentation modes, so like where structures tend to break, what kinds of patterns you might expect or ions you might expect to have happen there. And just to be clear, this won't be so free-form that you'll get a mass spectrum and no information about what it could be. And not to propose a structure like this, it'll be more like the first week of NMR, where you will have a set of structures that you'll assign each structure to a spectrum. So your problem solving is a little bit more constrained, which I think is more reasonable. So you should definitely feel free to work in small groups, either via Zoom, or I'm going to set up a discussion board on Brightspace. You're also welcome to ask office hours questions, or you can try to email me. Maybe we can figure out how to work that. And we'll see how this goes, right? So no one really has a great model for running labs remotely, but we're going to see if we can get this to work for us. All right, so that concludes the pre-lab video for mass spectrometry. Good luck with the exercises.